right, well, it is noontime, so I'm going to get started. Are there any questions that I can answer before I start today's lecture? Yes?
What is today? Is today's lecture going to be based on set theories and other things that you posted in Canvas, or is
Yep.
it going to be something new?
Nope. It's just, going in the order that I put stuff onto Canvas. I took one of these links out, because I thought, it's poorly written, like, never mind, just not read that. So we'll start with Boolean operators, which I think the whole class should be familiar with. It's just a review of stuff that you know already, except for two new operators. But we define those operators using operators that you know already. So hopefully it's not going to be, really difficult. We might have a chance to move on to basic set theory today. I'm not really sure how far we can go today. So I guess we'll find out. How many people took the 16 personality test thing? Okay, about half the class. So did you guys find it useful? You find it totally useless? That's not me, or was it creepily accurate?
It was creepily accurate, but it was too much thrown at you, though.
Too much what?
It was too much thrown at you, like, because
okay.
Sometimes you would find yourself, you'd be like, I'm like this on a Monday, and I'm like this on a Tuesday, but I was like this when I was a kid, but now I'm like this when I'm an adult.
Yeah.
So, but it's accurate, but you grow and change. That was the only problem with it.
Okay. Well, you have to answer those questions, with instinctively what your preference is instead of what you think you want the preference, to be.
Right.
So, and that I don't think we changed that very quickly over time.
Right.
So we change behavior, but not so much the personality. So as we learn more things, we change the way we do things. But inherently, we are still basically the same people, as we were when we were kids. That's my belief. Yep. But as far as this class is concerned, the only reason why I want you guys to take that test is to kind of understand yourself a little bit better, and also, it might help you to strategize, like how to study for this class and your other classes. So that's the only purpose. All right, so we'll start with a Boolean operator, and this one, taking a class from TAC, is if you believe in 16 personality stuff, read that one, because it might give you some insight of how you interact with me, and and it also I hope that it will help to resolve misunderstanding, on at different levels, so that you will understand, okay, so TAC doesn't really talk about emotion much. That sort of thing. All right, so we'll start with operators, and hopefully this is not going to be very time consuming, because even though I changed the presentation of operators may be a little bit new, but it's the same operators nonetheless. And today is one of those days when I think this is going to be helpful. So I'm going to use my tablet for in-class examples, and I need to change my tablet to fire up the right application first. Lecture notes. So this is really useful, because before I would record my lecture, everything in the projector as well as my voice is streamed to YouTube, but then everything that I write on the whiteboard is staying in the classroom, right? It's not uploaded, it's not streamed. So these days, I'm using my tablet in conjunction with a Chrome app. Okay, this is actually a Chrome app, which is kind of interesting because it's an extension out of a browser. And what it can do is it can help me cast the screen of my tablet to the screen here. Okay. And there we go. So this way I can use the tablet, as my virtual whiteboard. So everything that you see on the projector is actually going to be recorded as well. So it really helps from that perspective. So I'm going to go back to cisp440. Okay. And that's from the previous semester. I can always erase that later. All right. So Boolean operators. The first one is conjunction. Are there any questions about conjunction or about how we present conjunction using this truth table? And by the way, this symbol here, okay, it is introduced a little bit later. This particular symbol means and conjunction, but it's the mathematical notation instead of being C++ or spelling it out as A and D. How many people have seen this symbol in the context of conjunction? Okay, cool. In what class?
3 times.
Thanks. Besides classes that I teach. Linear algebra. Okay, so in a math class basically. So it may not be. It's not an extra thing. I think for you guys to get exposure to the mathematical notation of conjunction. So this table is really clumsy because what it does is it lists what happens when you have the independent variables x and y. The columns are corresponding to what happens when x is 0 versus when x is 1, and then the rows are corresponding to y of what happens when y is 0 and also when y is 1. So when you look at the intersections of each column and a row, that is the case when when x is this and y is this, what happens to the conjunction of x and y? Is that okay? So I'm going to pick one particular cell and use it as an example. So we'll take a look at this one here. So when you're looking at this particular cell, it corresponds to the column where x equals to 1. It also corresponds to the row where y equals to 0. So that means this is the result of the conjunction when x is 1 and y is 0, which also means that 1 and 0 is 0. Is that okay? So this is a really clumsy way to make a truth table. So we'll have a kind of easier way later. So this is the easier way to do a truth table. Basically, I'm just listing x is corresponding to these two. So x would be the columns, and then y would be the rows. So instead of spelling out x and y equals to something, I'm just indicating the result of the conjunction. So is that okay too? All right. And then the rest of this particular section just talks about the different ways to denote conjunction. This one I think you guys should know already, because that's your C++ notation of conjunction, or the AND operator. But you have to be careful that this is a double ampersand and not a single ampersand. There is an operator with just one single ampersand. It means bitwise not. Bitwise AND, but not logical AND. Okay, we're not going to use bitwise AND in this class. Well, maybe until a little bit later when we actually want to implement programs. But as far as logic is concerned, the conjunction operator corresponds to ampersand, which is the logical operator. Is that okay? All right. In mathematics, it is using this little kind of like a TP or inverted V symbol. A lot of times in other fields like engineering or electrical engineering, they also use multiplication to indicate conjunction. So x times y with a dot, can be used to indicate x and y. Sometimes it's even simplified even more, where it's just x, y. Is that okay? All right. So when you turn in homework assignments in this class, as long as I understand it is conjunction, you don't have to stick with a particular way of expressing conjunction. You can use C++ way. You can use the mathematical way. The HTML editor in Canvas is capable of equation editing, so you can actually use the mathematical symbol. But I would just recommend you to use the notation that I'm highlighting here, because it requires the least typing. Okay, so that's good. Do we have any questions about conjunction at this point? No questions? We good? All right. So the next one is disjunction or. Okay, so we're using the more simplified way of making a truth table. So once again, x are the columns and y are the rows. So this column is corresponding to what happens when x is 0, when x is 1, the rows are corresponding to values of y. What happens when y is 0? What happens when y is 1? So when you look at the intersection, it is corresponding to the value of x and the value of y.
So what is the diagonal?
The diagonal is just saying what is the rest here. Okay, these 4 is corresponding to actual value of the disjunction.
Okay, so that's intersection or that's just value?
Correct. So this one is 0 or 0 is 0. This one is 1 or 0 is 1. This one means 0 or 1 is 1, and this one means 1 or 1 is 1. Is that okay? All right. So now we look at the notations of disjunction. You have your C++ notation, which is x bar bar y. Okay. Remember there are 2 bars instead of 1. There's the mathematical notation of using something that looks like V but is not really V itself. And then there's also the notation that a lot of electrical engineers would use, which is using the plus symbol to mean disjunction. Is that okay? All right.
These are the or statements, right?
These are the disjunctions, yes, just regular or, yes. So are we still good so far? Okay, the next one is negation, which is not. Okay. So not is really simple because, so we still have the columns corresponding to values of x. Except in this case, this is, if x is 0, then not x is 1. If x is 1, then not x is 0. Because there's no second operand, so that's why the truth table looks kind of funky. Are we okay so far? Okay. All right. So down here we have the alternative notations. So in C++, we have the exclamation point, meaning logical not. It is not the tilde symbol. The tilde symbol is also a not operator, but it's bitwise not, which we do not use in logic context. The next one is the mathematical notation, which is kind of like a cliff. It's kind of like a line, and then you have a little drop, at the end. In engineering or electrical engineering, particularly, you will find the alternative negation symbol of a bar over bar, indicating this is basically, instead of in statistics, this is the average of x. In electrical engineering, in the context of logic, this means the negation of x. When you look at circuits or chips and stuff like that, negation sometimes can also be preceded by a single slash. So slash x is actually not x. But this one applies mostly to schematics and the way integrated circuits are documented. Like, okay, what does this pin do? Okay, then they would use this notation. Are we still doing okay so far with this? So for convenience in this class, I would just kind of use xy to mean x and y, x plus y to mean x or y, and then exclamation x to mean not x. Okay, because that requires the least amount of typing, and you don't have to get into the equation editor in Canvas. You can do it, but it's just kind of time consuming. Any questions at this point about the 3 operators that you already have learned in CISP 360, 400, and most of your other programming classes? No questions? Okay, so we're going to define 2 more operators. Possibly more. This one is called a NAND operator. NAND stands for negated AND. Okay? So the definition of NAND is just this. This arrow up arrow symbol, is what some people use to represent NAND. So x NAND y is really the negation of x and y. Is that okay? Okay, does everybody understand the definition of NAND? It is the negated AND operator. So you first perform the negation, you first perform the conjunction, and then you negate the result of the conjunction. Yep.
So in other words, it's saying that if I do this activity first and we negate the one that's in parentheses?
Well, let's see if we can work out a truth table for negated AND. Okay. So to answer that question, we'll do this. Okay. And let me see if I can make this a little bit bigger. Because right now it's not. Oh, okay, you can zoom. Good. All right, so we want to look at a truth table, and this time I'm going to use a slightly different way of making a truth table, where we have x, we have y, and then we have x and y. Then we have the negation of x and y, which is also known as, by definition, x NAND y. Is that okay? So we have 1, 2, 3, 4 columns. Is that okay? X and y are, okay, x as well as y, I should say, because and is kind of special in this context. So x as well as y are independent variables, which means the value of x doesn't really change the value. The value of y does not depend on the value of x, and vice versa. So that means we have 4 different combinations, because x can take on the values of 0, which in this class also means false. X can also take on the value of 1, which in this class means true. Is that okay? But while x is false, y can be true or false. So that's why one way to configure the values of x and y is both of them being false, or we can have x being false, y being true. When x is true, which corresponds to the next 2 rows, y can also be false or true. So this enumerates all the possible combinations of values of x and y, because each one can either be true or false. So this basically exhausts all the possibilities. Are there any questions about why I filled up these 2 particular columns in this way? Questions? Okay. So what about x and y? When x and y are both false, what is x and y? False or 0, okay? And the next one is false too, because if at least one side of a conjunction is false, the conjunction is false. Is that okay? But the next column is going to negate this column. In other words, everything that is false in this column, in x and y, is going to be true, and vice versa. So it becomes 1, 1, 1, 0.
So it's basically.
Okay, now I'm gonna ask, how did you get the numbers in x, and how did you get the numbers in y now?
X and y are both Boolean variables, and they are independent.
Right.
So that means when x is false, y can be false or true. When x is true, y can also be false or true.
Right.
So that's why we end up with 4 of these.
Okay, because I was just wondering, how did you get the, because x and y didn't have any sets, so I was just wondering, how did you get the true and false statements in that pattern there?
You mean the first 2 columns?
Yeah, the first 2 columns with the x and y, I just wondering, how did you get the 0 true?
It's just a possibility of
The complete set of 2.
Oh, okay.
All the possible combinations.
Oh, okay, so I can go 0, 0, 1, 0, I can make up my own, or is it going to
You can change the order, but this is the more kind of regular order, so it comes in a particular way that is easy to generate. You can certainly randomize it. You can say 0, 0 on one row, and then the next one is 1, 0, and then the next one is 1, 1, and the last one being 0, 1. As long as it is exhaustive, your truth table will still be okay. But if you have a more systematic way of generating this pattern, then when we get to 3, 4, 5, 6, different independent variables, we have a method to generate that. We can code it. All right. Is that okay? Now, what if I give you an assignment of generating this truth table using C++ code? Can you guys do it? Okay. The quickest and easiest way to do it is to use 2 for loops, one being nested in the other one. So one will be controlling the value of x, and then the inner loop will control the value of y, and then the body of the inner loop is going to be the one evaluating the conjunction, and then just print it out. Is that Making any sense? Okay. All right. Cool. So now we go back to the discussion here. So are there any questions about how the NAND operator is defined? It is just the negation of AND. Sounds kind of awkward because this is not one of the operators in any programming language that I know of. So why would I mention something that is totally not in a programming language? And yet this is a computer science class, right? Yep.
Isn't it used in memory, like ROMs?
You can use it in flash memory. Okay, there are circuitry that make use of NAND gates, you know, in ROM and other devices. But there's another reason. This is all you need. Yep. Go ahead.
So that all logic can be broken down into NAND?
All logical operators that we know of can be expressed using just the NAND operator. Okay? And how do we do it? You know, the 3 bullets, you know, explains how we do it. So if all you want to express is the negation of x, then when you take the NAND of x with itself, it gives you exactly the same exactly the same effect. In other words, if we have NAND, we don't need negation because we can do negation with NAND. Does that make sense to you? How do we know this? In a truth table, how do we know that the negation of something is really just that something NANDing itself? Okay, let me switch back to the slide here. So what you do is you look at the 2 rows where x, y have exactly the same value. The first row and the last row. Is that making any sense? Okay. So what you do, I'm going to change the color and also the thickness of the pen. So when you look at this row and you look at the last row, this shows us that basically by definition, x NAND x, 0 NAND 0 is 1. Right? The last row says 1 NAND 1 is 0. But isn't that just negation? So that's why we know we can look at this particular truth table and we can prove that x NAND x is the same thing as the negation of x.
It's a double negative.
Hmm?
Double negative on that.
It's not double negated. It really is just, you know, it's just a single negation.
No, I'm thinking of something else.
Okay. If you want to solve this or prove this by Boolean algebra, then you can go like, you know, x and x is really just x itself. So the negation of x and x, which is x NAND x, is the negation of x. So you can go that route as well if you want to prove using Boolean algebra instead of using a truth table. Is that all right? So the next one is going to be a little bit more involved. What if we want to express x and y, but you're only given the NAND operator? Okay, so you basically go like, okay, if we just want a regular AND, x and y, then you will start with x NAND y, which is the negated of x and y. This is close to what we want, but it is the opposite of what we want, right? So we want to negate that. But don't we know how to negate something already? In order to negate something, you just say blah blah NAND the same thing. So that's why we are also NANDing this with itself. And that becomes just regular AND. So we have just defined regular conjunction using NAND. The last one is disjunction. If you want to express OR, x or y, how do you make use of NAND? Well, turns out it's not that much more difficult. It is not x, NAND, not y. Now this one is a little bit tricky because it makes use of De Morgan's law. Okay, so we'll get to De Morgan's law, you know, later in this class, but I assure you that this works. If I say I assure you, or this is obvious that this works, you're supposed to ask, show it to us, or at least tell me how I can validate this by myself. So how would you do this? How would you validate this particular claim? Which is really kind of a big jump, right? I mean, this is a kind of a big jump because we have disjunction on one side, and then the other side is just a whole bunch of NAND operators. So how do you make sure that this does work out? How do you validate truth? Yep, exactly. Make a truth table. Okay? Because we know the definition of OR already. It's a little bit earlier in this class. But we also know what happens with NAND. So you just have to work this out one row at a time and then double check to make sure that whatever column is corresponding to X or Y has exactly the same value, row by row, as the column that is representing X NAND X, the whole thing NAND, Y NAND Y. And you will find that they are the same. Is that okay? So that means, you know, all the logical operators in C and C++ and all known programming languages, 2 are redundant of the 3. You really just need NAND. Now, but if you only have NAND, okay, expressing this conjunction or disjunction becomes kind of cumbersome, and that's why we like the other operators too. Is that okay? Now, if you take my cisp440, you will understand why NAND also has a special place, because it is one of those really easy logic gates to be implemented by transistors. 4 individual transistors can implement a NAND 2 gate. Okay. The next operator is implication. Now this one is really confusing in a way, but not so confusing in some other way. So it depends on how you look at it. If you look at it using the definition, which is basically saying X implies Y, is really defined to be the same thing as not X or Y, then it's not really too complicated, because all you're doing is you're saying, oh, it's just a simpler notation. Instead of spelling out not X or Y, we use, you know, X implies Y to mean exactly the same thing. So when you use not X or Y to define X implies Y, then the truth table is really easy to work out. So basically here we say, you know, X, this is 0, implies 0 is true. False implies false is true. This one says, you know, true implies false is false. This one here says false implies true is true. And then the last one, which is this one here, is spelling out that true implies true is true. And it is by definition. Okay, by definition, this is how we define implication. But does it make sense to you? Okay, I see a few people, you know, shaking their heads and they're like, no, it doesn't make sense to me. How can false implies true being true? The implication itself being true. Okay, it doesn't seem to make sense to some of you, but that's okay. Okay. So what we'll do next is to use some examples. So see if I can convince you that, you know, it does make sense from the perspective of, you know, just regular use of the word implication. Okay, let me change the font size here. Well, it's already using 18 points, so that should be pretty big already. We'll see. There we go. All right, so we'll say, now implication itself is a statement. It's not necessarily true itself. Okay, so let me give you an example of why I say that, you know, implication is really just a statement. So let's say this class, you know, pulls together. Okay, let's say we got about 40 students, and each person contributes $5. So the entire class, you know, pulls into a pool of $200. So you guys gave me $200 and say, okay, Tech, give us a statement. Give us a statement of wisdom, right? Okay, so I'll give you a statement of wisdom. Okay, so I'm gonna say if the sky is purple, everyone fails CISP 440.
What?
Take this
This
chance.
is my statement of wisdom. You just pay $200 collectively for this. And then of course, half the class immediately says, I want my refund. This is nonsense. And I go like, well, if you can prove that I'm wrong, I'll give you a refund. But if you cannot prove that I'm wrong, then I'm by default right. And you cannot get your refund. Okay? So let's see in which situation you do not get a refund and in what situation you do get a refund. Is that okay? But before we go any further, I'm going to rewrite this particular implication in the following format. The sky is purple, and put it in parentheses just to indicate that you interpret this phrase first. Okay? The sky is purple implies the rest, which is everyone fails cisp440. Okay. Is that okay? And in fact, I'm going to do one more. Okay, I'm going to go one step further and then use the implication symbol. Okay, I can approximate. Okay, I can approximate by using an equal and then a greater than symbol, like so. Okay. So now we have 4 scenarios, right? Because what if the sky is purple is false? What if the sky is purple is true? And then when the sky is purple is false, the other one being independent can be false or true. When the sky is in fact purple, the other one can also be false or true. So now our concern is tag wrong in each row?
Yes.
So if the sky is not purple, you look outside, the sky is kind of gray today, right? And you look at my roster and go like, last time the sky was gray, some people passed cisp440. Can you get your refund back and say, tag, your statement is false. The entire implication is wrong, false. You cannot get a refund, right? Okay. What about the next row? The next row says, well, last semester, on the day when I finished grading, the sky was blue because it was a good day, sunny day, and yet everybody failed in class. Can you get your refund back?
Yes.
No. Because my statement doesn't say anything about what happens when the sky is not purple. I only say what happens when the sky is purple. Then the following also needs to be true. So that's why you don't get a refund in this case either. Because my statement doesn't say what happens when the sky is not purple. All right? So the next one is the sky is in fact purple, and some people pass the class. Yep. This is the only time you get a refund. And then no refund for this one either, because this one is exactly as what the statement says. Okay, the sky is purple and nobody passes cisp440. Does that make any sense?
So these are pretty much like conditions.
Huh?
So these are pretty much like conditions. So
It's like what? Again?
condition.
Conditions? It is conditions. Yep. It's the first one is a sufficient condition for a segment. That's what it is. In other words, as long as the sky is purple, it doesn't matter how much you study, doesn't matter how easy the test is. Everybody fails cisp440.
Doesn't matter if you give us the answers.
Does not matter, because this statement says if the statement itself is true, it means it is absolute. If the sky is purple, then it doesn't matter what else happens. Everybody fails cisp440. But does that mean if the sky is not purple, then it is not possible that everybody would fail cisp440? It doesn't say that either. Yep. Okay. So now what you do is you turn the no refund to true, because if the statement itself is true, you cannot get a refund. And then the only case where you do get a refund is when the implication itself is false. So that's the only one when it is false. In other words, I'm giving you another truth table. Right here, but only in the context of when you can get your refund back from a random statement that I say, that I just spew out. Yep.
So when you get a refund, that means that you're saying it does not imply that.
Because you only get the refund when the statement itself is false. Is that okay? Why do you think implication is an important operator in this class? After all, that is not in a programming language. C++ does not have an implication operator. So why is this important in this class? So we're going to revisit this, from time to time, why implication is important, or there's a special place for implication. What is a mathematical proof? For those of you who have taken other classes in mathematics, what is a mathematical proof? What do you start with in a mathematical proof? Assumptions, axioms, okay? So you start with all the stuff that is either known to be true or told to be true. Okay, so because some math questions may say, assume da 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 da, prove the following, right? So what you're proving is a statement, okay? It is just a condition. It can either be true or false. What are the quote-unquote steps of proving a theorem? Not breaking it down so much. It's a change. Okay. But in each step, what are you doing? You're making use of what?
Implies.
Implication. Very good. So in each step of a mathematical proof is a implication. You're making use of a rule that is an implication. Okay. So so let's see if we can look at a mathematical proof from a perspective like a picture, okay, like a graph representation. So what happens is I'm going to make some dots here. Okay, so let's say these dots are representing everything that is known to be true, which can include the axioms. It can also include, in the question, assume blah 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 blah. So those are the black dots. Okay. Oh, okay. You're not seeing the black dots. Obviously, this is not a psychic projection screen, because otherwise you would see it. Okay, psychic paper, psychic, stuff as in from Doctor Who. Okay, do you guys watch Doctor Who?
I watch Doctor Who.
Yeah. So do you remember, when he needs to go into some building, he would kind of flash his psychic paper. And what does a psychic paper do?
Lets people see what they want to see.
Yep. But sometimes it can also work the other way. He can project it too. Okay, so never mind if you don't watch Doctor Who. Okay, so this green dot over here is the actual theorem that you want to prove. So what is happening here? What are the steps of proving a theorem? So what happens is you're using implication. So this may be something that is implied by this thing and this thing combined can imply this. This thing and this thing combined can imply this. This and this together can imply this. I'm just making a very simple case here. And then these two combined can imply the actual theorem. So every single step in a mathematical proof is an implication, or making use of an implication that is known to be true. Is that okay? And that is why implication as an operator is particularly important in this class. Okay? Because if an implication as a statement is known to be true or given to be true, then it becomes the basis of a proof. Is that okay? We'll come back and touch on this later. Okay, whenever possible, we'll get back and talk about this. And then the last operator is called equivalence. So equivalence can be defined using implication. So when we say x is equivalent to y, it really is saying that x implies y and y implies x. But since we just talked about implication, we can actually understand this part too. the truth table of equivalence is actually quite easy, because in this case, x is equivalent to, 0 is equivalent to 0 is true, 1 is equivalent to 1 is also true, but if they're different, then the whole thing is false. Okay, I guess the projection screen doesn't go all the way down. Now it does. Yep.
Is it okay to rephrase this as if and only if? Or
Yes. So equivalent to is also known as if and only if, or IFF.
If and only if.
If and only if. So it does go back to the conditional statement in C++. Okay, so
If and only if is the truth values of both of the different variables have to match with each other.
correct. If and only if expression is true, then the two sides have to have the same Boolean
as far
value.
as like when looking at the table.
Right. Okay. So now it's a good time to look at something that we should have understood already, but do we really understand it? So I'm going to give you a conditional statement in C syntax. Okay. So I'm going to say if x is less than y, then z gets 2. Okay, doesn't have an else branch. What does that mean? So when you execute this particular conditional statement, tell me what happens when x is in fact less than y. Then z gets a value of 2 for sure, right? Okay, cool. So now the question is, what if x is not less than y?
Z doesn't give it value.
Garbage.
It doesn't see
So there are two answers now. Those of you who are loyal to your C++ class and your C++ knowledge will say, if x is not less than y, nothing happens for sure. Right? That's how we use conditional statements. But those of you who just absorb implication will say, we don't know what's going to happen when the condition is false. It doesn't say anything about what to do when the condition is false. Yep.
I think I heard the same answer faster unless the Z gets a garbage variable otherwise.
No, it's simply we don't know what's going to do. We don't know whether it will execute the statement or not. Because if we change the words a little bit, if blah blah blah, then something it's the same thing as the first thing implies the second. Okay, so this becomes x is less than y implies that we will change z to 2. Yep.
Well, like in mathematics, if something's not true, then the theorem doesn't apply. Isn't that more clear? If this isn't the case, then this operation will apply.
But then are you going to do it or not? Remember in the truth table, when the first part of an implication is false, we don't really care about the second part, because the whole thing will still be true. So in this case, if x is less than y is false, and we go by the strict definition of implication, then we don't know whether z equals to 2 should execute or not. It is correct either way, because of the way we define implication. Yep.
So are we looking at this in particular in the context of C++ or just in the context of
In the context of implication. Because when you look at this, okay, the other way to say this is x is less than y implies that we should do the following operation, z equals 2.
Alright, yeah, so anything could happen after that.
Exactly. So when x is not less than y, we don't know whether it's right to perform this operation or not to perform this operation. It's acceptable either way. So how do we fix this? How do we fix the way we represent conditional statements so that it is spelled out so that, if the condition is true, yes, go ahead and execute z equals 2. If the condition is not true, do not execute the statement. How do we change it?
Add else functions.
You can add an else, but you can also just do this. If and only if. In other words, computer science people have been using the word if wrong for decades. It should have been if and only if x is less than y, perform this operation.
Oh, that won't compile, right?
Hmm?
That won't compile, right?
It will compile
Really?
if you just do this. Then it's all cool again.
The universe is breaking. Hold on for a second. There you go.
Yep. All right. So don't mention this to your C++ teacher. Okay.
Oh no, I can't mention it. They put me through.
Text said that everybody who invented programming language have been wrong up to this point.
Yeah, this is revenge. I'm hella mention this.
So are we good so far with all of these operators? Conjunction, disjunction, and or, negation, which is not. And then the only new operators that we introduced today is NAND, the negation of a conjunction, implication, and if and only if. So those operators are new. Now implication is insidiously useful in this class. And I use that word because we use that word, and most people would just say, oh, okay, blah 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 implies something, and use it kind of in a much more casual way. But every time I use implication, every time I use that symbol of implication, it has this specific meaning. Okay? All right. So I think we are ready to move on to basic set theory. So we're moving on right now. And nobody reminded me to check on the OBS to make sure that we are recording. This one says start recording. And then this one here. Okay, do we have another one? This one is recording already, so I'm pretty sure we are actually recording.
I did get a notification.
Huh?
I did get a notification.
Okay. You can actually watch the stream, like in class, and verify that it is actually recording with voice.
Because it's a few seconds late.
Yeah, it's going to be about 20 seconds late, but you can.
20? I thought it was a little bit faster than that.
Is it?
For me, like when I listen, it's like about maybe like 3 to 5 seconds late.
That's actually not bad. And we know that the audio is recording too because of this, meter thing. So it's all good. All right, so we're going to get back to Canvas. Actually, we might have it still open here. There we go. So now we're moving on to set theory. And some people may have exposure to set theory from high school or other classes. How many people have some exposure to set theory from other classes?
Well, no, it was a challenge for me to learn a certain amount of hours, and I did. That's the only exposure I have.
Okay, that's okay. It's not required. I'm just curious of how many people have some exposure to set theory already. All right, so set theory, as the name implies, is about the concept called a set. Okay, and it is easy to understand. It is also kind of hard to understand. Okay, it's easy to understand because all it really is a container, is a bag of something. Okay, but there are certain restrictions. It's kind of like an array, but it's not an array. Okay, so let's go ahead and find out what exactly is a set. So I'm going to switch to the tablet here, and then we'll go like, okay, so we'll say X is a set. Okay, so it is conventional, not always the case, but it's conventional to use an uppercase letter to indicate that it is a set, but it's not always the case. So in this case, I'm using uppercase X to denote a set. If you want to spell out the content of a set, you use curly braces to enclose the actual content of a particular set. So I'm opening here, and we'll just say, it consists of A, 20, uppercase Z, and 2, and then B. And then, okay, maybe uppercase A.
In this case, is the uppercase Z and uppercase A different sets?
They're considered distinct, yes. So there are several things here. One is we use curly braces to indicate what is inside a set. Two, we use a comma-separated list inside the set notation, inside the curly braces, to separate elements inside the set. So whatever you have, whatever the set contains, they're called elements. So in this case, A, lowercase a, is an element of X, 20 is an element of X, 2 is an element of X, and so on. But there's one restriction that you cannot really observe, is we cannot have duplicate elements inside the set. In other words, I cannot have another 20 after the uppercase A. Okay? The same value, everything inside the set have to be unique within the set.
And since the set of X, for instance, just as an example, has 20 in it, and then it has a set of Z in it, and then can Z set contain 20 or no? Can
Say that
20
one
also-
more time.
So 20 is within the set of X,
Mm-hmm.
and then the set of Z is also within the set of X. Now, can Z contain 20?
Z can be a set on its own and still be considered an element of X. Okay, so I think I understand what you're talking about. So you're talking about, this is X. Can an element of X being a particular set itself? That's what you're asking. Can a set contains an element such that the element itself is a set on its own? And the answer is yes.
That wasn't my question.
That wasn't your question. Okay, sorry, I misunderstood that.
No, I'm just saying it. Now let's set what's in Z, right? If
Mhm.
Z is another set of elements.
Okay.
Can Z contain 20?
Yes.
While 20 is also within X?
Yes. Mm-hmm. Yep, go ahead.
Can a set contain itself?
No. It cannot contain itself because, okay,
Well, it proves that. Couldn't you prove like if two different sets are the same, essentially? Like say set of U and set of X.
that's a good question then.
Because I
The
know in
question,
math I had to do that.
so the question is, when can you consider two sets being exactly the same?
Yes.
What do you think would be the answer?
Mhm.
When
When
do you,
also-
how can, okay, under what condition is set X equal to set Y? So we know that X is a set, Y is a set. How do you know these two are the same? Or if I say they're the same, what does it mean?
When all the elements of X match with all the elements of Y, when there's only one of each within.
And vice versa. Okay? So the answer is, it's actually in the notes, so you don't really have to write it. Okay, but it's a little bit out of order. We are talking about we're talking about the equivalence of two different sets. So a set can be compared to another set to see if they are the same. You cannot say one is bigger than the other one, but you can say one is whether they are the same or not. So we can say that the two sets are considered the same when every element in one is in the other one, and every element in the other one is in the first one. So that's kind of like a vague way of defining equality between two different sets. Yep.
Will it have to be in the same order?
No, order is not important with a set. Okay, so that's a very good question. So now, if I switch back to the tablet, I can now say this particular set, A, B, C, is in fact the same as the set of C, B, A, because ordering does not matter. There's no order amongst elements inside a set. Order is insignificant in a set. And that's why it's different from an array where ordering is important. Yep.
No, you said a set cannot have duplicates in it. Like for the previous example when I was saying, like, let's say we have this set, which is the set of X, and then the set of Z, let's say it has different elements, and one of the elements is 20. Now,
Mhm.
because X also, because the set of Z is also within the set of X, and X X already has 20, and the set of Z also has 20. Isn't that like a redundance of the 20, or
Nope.
no?
Okay. So you can have a so if you go with this definition, you can still say that Z is a set on its own that has an element of 20. That's perfectly okay. In other words, X can be a set where a particular element has a value of 20, but another element is the set that has an element of 20. That's perfectly okay. Yep.
I think that's what you were saying, but you only brought one element within. One set would include one element within another set.
Okay, how about this?
Yes, that's what I was thinking.
It is valid. Okay? This is not valid. Because two elements are exactly the same.
Can you elaborate?
Yeah,
That could go hand in hand with the union, right? When you want to represent a set that is more simplified.
Well, a union is an operation on sets, yielding a new set. We'll talk about that too. But right now, we just want to know what is a set and how can we compare two different sets. Yep.
Jose, can you elaborate on the two that's inside the curly braces? We have the one that's valid and one that is not valid.
Okay, so the one that is valid is okay because 20 as an integer is considered distinct, different from a set that has the element of 20.
Oh, so the reason why you have that because it goes back to the rule what you said, all of them has to be unique.
Yes.
Oh, okay. That was my only issue when I tried to do some study on this.
Okay.
Yeah.
So one way you can kind of look at this is folders. So consider a set as a folder.
Okay.
Okay. Can a folder contain other folders? Yep, it's okay. Can a folder contain two files of exactly the same name?
No.
No. Okay. So that kind of explains it. There's no inherent ordering either in this kind of folder, which is not exactly the same as a regular file folder because a folder in a computer sense, is usually sorted by file name. Is that okay? So if you have a file, okay, inside a particular folder, that folder itself is not considered the same as the file that it is containing. Well, same thing here. So the value 20, the integer 20, is considered not the same, not equal to the set containing the value of 20. And that's why it is okay to have a set that has one element being 20 itself, another element being a set that has a single element of 20. So it is okay. That one is valid. So are we okay so far with this? Okay, very good. So we'll move on with the notes.
So would we refer the Z to be the subset of X? Or
Yes. Well, no. Z is an element of X. So in this case, okay. So in this case, Z is considered an element of X. That's a very important notation. So this particular notation, it looks like a funky E. It's called element of. You can say Z is an element of X here. You can also use the word in, okay, to be short. You can say Z is in X, which means exactly the same thing as Z is an element of X. But that particular symbol is important. Yep. Mm-hmm.
So in other words, when you say Z is the element of X, that means because they both contain 20.
Nope. Nope. It has to do with Z.
Oh, because
it's actually an element of X.
Okay.
Yep.
I'm stupid.
Oh no. This is confusing stuff. So that's why we try to use examples to illustrate, the tricky cases.
All right, and another thing, so I can say Z is also the element of X as well, right?
Which one?
Z
is an element of
X.
Yes. Well, that's what.
Yeah.
What's it say?
Yeah, that's what I'm just. Oh, well, hold on. Let me get another one. Then A is the element of X.
Yes.
And like it's okay, cool.
Yep.
So if Z is the element of X, can Z have X in it?
Not uppercase X.
Can't have uppercase X in it?
No, because a set cannot contain itself. Is that okay? It's kind of like a folder cannot contain the folder itself, or a subfolder of a folder cannot contain that folder.
Shortcut to that folder.
We don't have shortcuts in set theory.
Oh, come on, where's your fancy trick at, man? I need one for C++.
Well, if you really want to talk about shortcuts, then you have to talk about soft link versus hard link in the file system. What we understand as a shortcut is usually a soft link. A soft link, is actually okay. You can have a symbolic link inside a folder back to itself, but not a hard link. Okay, but are we still doing okay so far with all of this stuff here? Okay, now I have to emphasize this notation here. Z is an element of X. This is a statement. It can be true, it can be false. In other words, I can basically say something like this. I can say 26 in X. Okay, it's a statement. It is just, it's just like X is greater than Y. Is X really greater than Y? Maybe, maybe not. So in this case, the question is 26 really an element of X?
No.
In this case, it is not, right? So then we say this is false. In other words, element of or in is Boolean. It's a Boolean expression. It has a value of either true or false.
So the expression E is element in?
Element of or
Element
in.
of.
Yeah, either way is fine. So are there any questions at this point? Just about the element of notation, or how we spell out the inside or the elements inside a particular set. Yep.
So if a set is an element of another set,
Mhm.
then you cannot take the elements of that inside set to expand them out as being part of the main set. Like if 26 was in A, for example, you cannot say that 26 is an element of X. It's an
That
element.
may be true as well. Okay, so I'll explain why. Okay, so I'll give you this case here. I will say X is defined to be 20, the set of 20, the set of the set of 20. Okay? Is that okay?
Yeah, I guess so.
So in this case, 20 is an element of X is true. The set of 20 being an element of X is also true. The set of a set of 20 is in X is also true. So it depends on whether those are actually element inside X or not.
Aren't you duplicating values at that point?
Huh?
Aren't you duplicating values at that point?
There's no duplicate. There's no duplicate whatsoever. This is basically saying I have a folder where inside the folder there's a particular file, but there's also two more folders. The second folder has the same file as in the root of this particular folder. Is that possible?
Yes.
And then the third folder has a single folder inside of it, and inside that nested folder is the same file that you have at the root level of the first folder. Is that okay? Perfectly doable, right? That's exactly what this situation is. Is that making any sense?
Yeah, it makes sense.
Yep. So if you think about a set as a folder, it's a container, okay? Then it makes sense because a container can contain other containers. Yep.
So the E operator is non-recursive. If you remove the
It is not recursive. That is correct. The element of operator is a single level check.
right.
Is this thing in this container? It doesn't check if that thing by itself is a set. It doesn't check what is in that thing.
Right. Okay.
Yep.
Makes sense.
So, for instance, if let's say within a set of X, I subset within the set of X where 20 is just the one layer set within X. Like let's say if it was 14, because you said it's just a single gate check,
Mm-hmm.
we wouldn't be able to then, by that logic, declare 14 as an element of X. We would need to say 14, or the set of 14 is an element of X.
Okay, so let me see if I get your idea. So you have 14. Let's say this is a set of 15, and this is a set of a set, and inside which we have 16. Okay? So in this case, 14 is an element of X, is true. 15 is an element of X, is false.
So it's just
But the set of 15, a set containing 15 by itself is an element of X, is true.
Yeah, I think that was what I was wondering about.
Questions? Any questions at this point? Any scenarios that you want me to kind of run through? Yep.
So I think what you're saying here is that 15 is not actually equivalent to the set of 15.
That is absolutely true. Yep. 15 is not considered the same as the set of 15. Yep. All right. Are we? Yep. Go ahead.
What if instead of X, there's a set of A and B, and B and B is set of 20, the same. They have the same set.
Okay. So let me see if I can. Let me see if this is what you mean. So you have a set A, which is defined this way. Okay. So A is a set which has a single element of 20. B is defined the same way, okay? And then you have X being a set of A, B, right? X is not a valid set in this case because they boil down to the same element. Because a set with an element of 20 and a set with an element of 20 both set. These two are the same because every element in A can be found in B, and every element in B can be found in A. So these two are considered the same. So when they're the same, they cannot be listed separately as elements of another set.
So that means you cannot do X and A and B. You cannot do that third set, can you?
So it is invalid.
Okay, so that was invalid. Okay. That saved me a lot of time. I'm about to be scared. Like, oh my goodness, there's some equations.
Yeah, so it's important for me to indicate this is actually invalid. You cannot call X a set. Yep.
So let's say B wasn't part of X, right? Could we then say that the
Let's say B is not what again?
yeah, B is not in it. So X is
Just A? Just A?
another, yeah.
Yeah.
Could we say that the set of 20 is an element of X?
Yes.
Okay.
Because A is really just a symbol representing the set, a set that has a single element of 20.
Okay.
Yep. So do you guys have any questions back there?
I was just asking about how the folder analogy works here.
A folder analogy?
Yeah. I'm saying it still works. Well, yeah, so
folder
it's like,
analogy.
you can have the separate folders A and B, I guess.
Right.
But and then so
Yep. So in the case of a folder, that won't work.
yeah,
Yeah.
unless you consider the name of the folder to be the contents.
Yep.
Yeah.
Yep. So it won't work in the case of a folder in this case. Yep. Okay. So are we okay so far? All right. Okay. So now we are moving on to. Yeah. Go ahead.
Sets within sets. If obviously the order doesn't necessarily matter. but
The
if
order
A
does
had-
not matter at all.
If A had a series of whatever information and then 20, and then B started at 20, and then other non-matching information with A, would it still be invalid?
Okay. Say that one more time.
So if A was like, I don't know, X2, 3, Q, and then 20,
Okay.
and then B was 20, and then it was, exclamation point, pound sign, and then some other garbage. Basically, the only thing that matched between those two sets was the 20.
Okay. I see. I got you. Okay. So we'll look at this. Okay. Okay, is that an example that
Yeah.
illustrates what you
Yeah,
wanted to
the
say?
only
Okay.
thing that matches is 20.
So now, is A and B the same?
No.
They're not the same. Why are they not the same based on what we just talked about? Exactly. It is not the case that every element in A can be found in B, nor the other way around. So if A and B are distinct like this, then you can have A as an element and B also have being an element of the same set because they are not the same. They're distinct.
You know, they carry at least a partial amount of the same.
Yeah, but they're not the same. They're not the same set
Not identical.
anymore. They're
Yeah.
not identical. They can overlap, but they're not the same set. So that's the whole point. Is they're not the same set, and if they're not the same, then they can be elements of another set, a containing set. That's an interesting. That's a good question. Yep.
Can you like rename set to be like set C equals set A plus set B minus 20?
We'll get to those operators later. Okay, we don't. I understand what you say plus, but we don't use the word
I figure we
plus.
don't, but you know what I mean.
It's called a union.
Right.
Okay, when you want to have a bigger set that is based on the elements of two smaller, potentially smaller sets, it's called union. Yep.
So so element XAB is valid if there's difference in
Correct.
the A and B. Okay.
So in this case, it is invalid. In the other case, is valid. Okay, so if I break the screen into two halves, if A is defined to be just a set of 20, B is defined the same way, then X being a set of AB is invalid because A and B are in fact the same thing. On the other hand, if A and B are different, they do have an overlap of 20, but they're not the same. In that case, you can have a overall set X containing A and B as two different elements because they are in fact different. Yep.
So as long as there's one different element in the sets,
Mhm.
it's okay.
As long as there's at least one element that is found in one but not in the other one, they are distinct. Okay, so let me explain what I said with that one. So we'll say X A is AB and B is ABC. Okay? A and B are still considered different in this case because in order for A and B to be the same, everything in A has to be found in B, which we got here. But vice versa has to be true too. Everything in B has to be found in A. That is not the case because C is only in B but not in A. So now A and B are now considered distinct, they're different, and they're not the same. Yep.
Okay. So I was wondering. So let's say we do X right with A and B. Does the value change, or is A still worth A and B is still A, B, and C?
They're the same. A is just by definition the set of AB. B
Okay.
is by definition the set of ABC.
Right.
So in this case, X is by definition the set of AB as one element,
Right.
the set of ABC as another element,
Right.
and it is valid because the set of AB is different from the set of ABC.
So like, let's say if I want to extend this out, so it would be like A, B, and C for A, and then also A. For A, it'd be A and B, and then for B, it'd be A, B, and C. If I want to decide if I want to extend it out, so A and B is still the same value as A and B. In other words, I'm saying it does A is equivalent to saying A and B is equivalent to A, B, and C. It's inside of the open inside of X. Inside of
Right.
X.
So
Okay.
this is in fact the same as. I'm not sure whether this is what you mean.
Yeah, that's exactly what I mean.
Yeah, because I unfortunately I
Yeah.
chose the wrong letters to use because I use uppercase and lowercase a. So when we say just A B, I don't know whether you meant the set A or
Oh,
the
my
element lowercase a.
No, that was it. What I want to write for my
Yeah,
notes.
they're the same.
Okay,
Because
cool.
A is by definition just that, so you can expand it. B is by definition ABC, so you can expand it to the elements ABC. But now the question is the set A related to the set B? The answer is yes, okay? But we haven't talked about that particular relational operator yet, okay? It's called a subset of, okay? We'll talk with, okay, so here's your reading assignment.
Reading something?
reading assignment. So you have to read ahead of me. And let's see, where are we?
Whoa, I saw Sigma.
Yeah, so read this before Wednesday. Okay, so I want all of you to finish reading basic set theory and potentially the next one. If you have time, go ahead and read the next one too, because that's going to be beneficial when we get to that one. Okay, so we are currently here. We are, I would say, maybe halfway through the basic set theory. So I want you to definitely finish reading basic set theory. But if you have time, go ahead and read the next one too, basic quantifiers. Okay, because quantifiers and set notation, they're kind of related. One really can help with the explanation of the other one. So I want you to kind of read on to the next one. This is kind of like a homework assignment. It's not open yet, so don't worry about it. I'll open this up as soon as we're done with basic set theory. Okay? Right? Because I've done it 7 times. Okay, office hours. To find my office hours, you go to the syllabus, and it is listed there.
Okay, yeah. And the reason being is because the thing is, I just have some theoretical and some application questions on them when we do the homework assignment, because like I go over it like twice online, and then the way how online this place is kind of weird. So I just have like some questions on some symbols.
Okay. Yep. So go to the syllabus, find out when I'll be where, and then I'll see you.
Hi there.
Yes.
So I didn't know there was an 18 unit cap, so I had to go put in one of those submissions to take more than that to add.
Oh,
so
okay.
Yeah.